We usually think of gravity as a force between objects with mass. It's easy to see how this force works by stepping on a scale to see how much you weigh. The number on the scale represents the Earth's gravity on your mass, or your weight on planet Earth. When it comes to gravity in the cosmos, we can imagine the Sun's gravity keeping the planets in their orbits, and we all know about the strong gravitational pull near a black hole. The so-called force of gravity is easy to understand, and gravity might seem like a simple thing after all. But things are different in the current age, as we know now that gravity as a force is only a small part of a more complex phenomenon thanks to the general theory of relativity. But before we get into that, it's time for a little Physics 101. Everyone is familiar with Newton, who was a veritable demigod of physics during his time, and the story about the apple falling on his head. Well, that didn't really happen. The truth is, Newton saw an apple fall from a tree and was in a contemplative mood. At that moment, he wondered why the apple fell straight towards the ground, and not sideways or in another direction. He presumed that a force of gravity between two bodies pulled them towards each other with a magnitude directly proportional to their mass, and also inversely proportional to the square of the distance between them. The path that the bodies take will be the shortest to minimize energy use, therefore a straight line. In short, Newton believed an apple falls because a gravitational force accelerates it towards the ground. Newton probably thought there was something missing from his theory though, because it said he wasn't completely satisfied with it. This is because he originally thought of the force of gravity as a push, not a pull. Little did Newton know that he was partially right about this, but his theory of gravity was accepted as gospel, that the magical pull was an essential property of mass, the theory which withstood and obscured the truth for the next 400 years. That was until Albert Einstein, another formidable genius, came along in 1905 and presented his general theory of relativity while working as a Swiss patent clerk. His challenge to Isaac Newton's theory was either ridiculed or ignored completely, because his ideas seemed too radical to be possible. The key to understanding the theory of general relativity is that everything in a gravitational field falls at the same rate. But it wasn't Einstein that figured this out, it was Galileo that first concluded that all objects released together in the absence of an atmosphere will fall at the same rate regardless of their mass. A famous experiment by Apollo 15 astronaut David Scott was done on the moon to test this theory. At the same time, moonwalker astronaut Scott dropped a hammer and a feather, and they both glide to the ground and impact the ground at the same time. The same thing would happen for any object regardless of its mass or its physical makeup. This is known as the equivalence principle. So why do the two objects fall together and land at the same time? It's because they're not falling. They're standing still, and there is no force acting on them. With Einstein's theory, gravity is not a force between two objects with mass. Instead, gravity is the warping of space and time in the presence of objects with mass, and without some force acting upon the objects, they will travel in a straight line. Einstein believed smaller objects are not pulled on by more massive objects, but instead the objects are being pushed down by the space above them, and that there is no such thing as a gravitational force. According to Einstein's theory, matter warps not only the fabric of space, but time as well. This is called space-time, and any object in space warps this space-time continuum. Space-time is the three dimensions of space: length, width, and height, combined with the fourth dimension, time. The more massive the object, the more it warps the space around it. Einstein believed that apples fall from trees and planets orbit stars because the objects are moving along curves in the space-time continuum, those curves being gravity. A good example to see how this works is to visualize the Earth on a grid of space-time. You can see the mass of the Earth warps space-time and creates a kind of gravity well. Any object around this mass, you, me, and even the moon, is pulled down and towards this gravity well. The moon also warps space-time with its mass, but the gravitational field between the Earth and the moon is not strong enough to pull the moon towards us. Instead, it's also like an apple falling from a tree. The sun also has a huge gravity well that keeps everything in our solar system from flying off into space. We can also understand how gravity wells around planets in our solar system work by how we've launched spacecraft. To get spacecraft moving in different directions from their launch path and increase their speed, engineers used warped space-time, or the gravity around other planets in our solar system, to get a gravitational slingshot that sends the spacecraft in another direction with greater speed. The closer to the planet, and therefore its gravity well, the faster the object will begin to move. What it all comes down to is that objects in the universe are attracted to each other because space-time is bent and curved. The closer they are to the object of mass, the faster they will accelerate. But what about this so-called gravitational field we were talking about earlier? Is it not a force? A gravitational field is actually the force field that exists in space around every object with mass. The Moon has a smaller gravitational field than the planet because of its mass. The Earth has a much stronger gravitational field over the Moon because of its mass. But in space, a gravitational field exists almost everywhere. With everything floating in space above our heads, it might be easy to believe there is no gravitational field at work in orbit around our big blue planet. However, even the International Space Station feels the gravity of Earth. The surprising thing is, the effective gravity in orbit around the planet is nearly the same as the one on the surface of the planet. In fact, it's about 90% as much in orbit as on the surface of the planet. So if you weighed 100 kilograms on Earth and had a space ladder that reached all the way to the space station, you'd weigh about 90 kilograms up there. But wait a minute, if there is gravity in space around the planet, why do astronauts look like they're floating around in zero gravity? The reason astronauts look like they're floating in space is because everything, including the International Space Station, is falling together at the same time in the vacuum of space. This condition, in which it appears people and objects are weightless, is called microgravity. If everything falls in the same way regardless of its mass, then a free-floating astronaut far from any gravitational source and a free-falling astronaut in the gravitational field of a massive body would each have the same experience. In fact, the space station, satellites, and everything else up there is always falling towards the Earth. And while the International Space Station is falling, it's also moving very fast, at about 28,000 kilometers per hour from the pull of the Earth's gravitational force. There are some ways to prove Einstein is right about objects with mass warping the fabric of the universe called space-time. The gravitational acceleration at the Earth's surface is 9.81 meters per second. The reason gravity pulls you and other objects towards the ground has nothing to do with the core of the planet. All objects with mass bend and curve space-time, and that curvature of space is gravity itself. So if you were to somehow make a journey to the center of the planet, there would be no gravity. You would be away from the curvature of space-time at the center of an object with mass, and therefore floating around the core of the planet weightless. But as you started to make your way back to the surface, you'd start to feel the curvature of space-time from the mass of the Earth, and the effect of that curve, gravity, would start to get stronger. Of course, we'll have to get a probe to journey to the center of the Earth to nail that one down. But there is another way to prove that gravity warps space-time. One of these things is called gravitational lensing. This happens when a massive celestial body causes a big enough curvature of space-time that the light around the object appears visibly bent, as if you were looking at a camera lens. This gravitational lensing happens when the massive object, such as a galaxy, warps the space around it into rings of light. Interestingly enough, this has helped us find other galaxies and objects in space that we wouldn't otherwise see without the gravitational lensing effect. Einstein's cross is a famous example and shows a gravitationally lensed quasar that sits directly behind the center of a galaxy. 4 images of quasar appear in the foreground due to the strong gravitational lensing of the galaxy in the middle. It might seem like Einstein has this whole gravity thing locked down, and there is a lot of evidence to support general relativity. But here's the big problem. In its current form, it's incompatible with quantum mechanics. Quantum gravity is theoretical physics that seeks to describe gravity according to quantum mechanics. As of now, there's no such theory that is universally accepted and confirmed by experience. But that's not all. Researchers understand that at some point in a black hole, Einstein's theory breaks down and stops working. Scientists used 3 giant telescopes in Hawaii to watch a blue star called SO2 make its closest approach to the black hole Sagittarius A star in the middle of the Milky Way galaxy in its 16-year orbit. If Einstein's theory was right, the black hole would warp space-time and extend the wavelength of the light from the star. The waves of light would stretch out as the intense gravity of the black hole would drain their energy and cause the light from the star to shift from blue to red. And just as Einstein predicted, the star began to glow red. Had it been another color, it would have hinted at a completely different model of gravity altogether. Right now, scientists are looking for a curvature of space-time that is so extreme, the theory of general relativity fails. They believe that in the next 10 years, the theory of general relativity will be pushed to its limits, and another genius will come along and show us where Einstein was wrong. Let's hope we don't need to wait another 300 years.